Okay, now we're going to go into the world of rotational kinematics. Very similar to linear kinematics, except now we're talking about, obviously, things rotating. Thanks, Captain Obvious. Now, first of all, in order to talk about rotational kinematics, we're going to have to talk about radians and degrees. In math classes and in physics, we're going to use radians a lot. We can also use degrees, and we need to be able to go back and forth between the two. The key thing is in one circle, it's 1 revolution. Now that makes sense. It's 360 degrees or 2 pi radians. And we just usually write rads. So when we're talking about, whenever we're talking about an angle of pi or pi over 2 or something like that, what we're actually talking about is part of the way around a circle. Remember, 360 degrees is equal to 2 pi. And of course, we also know that circumference is equal to 2 times pi times the radius. So those are going to be used to help us a lot. So we'll have to be able to go back and forth. So for example, if I wanted to say 90 degrees was equal to how many radians, well, I simply go 90 degrees. And again, I'm going to multiply by 1, but I'm going to choose wisely. I want degrees on the bottom. I want rads on the top. Make that fraction equal to 1. I get 2 pi divided by 360. So that becomes 1 over 4. So I get 2 pi over 4 rads, which is, of course, pi over 2 radians. Okay. A radian is nothing more than 1 radius out on the circle, the edge of the circle. So don't let radians confuse you. That's all really a radian is. Okay, now everything that we talked about in the linear world or the translational world. We use those, you'll see those words used interchangeably. Linear and translational means 1 dimension. I guess it could also mean 2 dimensions. And then we'll have angular, or you'll oftentimes see it called rotational. Again, you can really use either term when you're talking about it. So be careful about it. Well, we know that we had one variable we talked about a lot is displacement. Well, there's a linear displacement and there's also an angular displacement. Linear displacement, well, that's what we called x or delta x. It may show up as some teachers use S, some people use D, some people use R. I'm not 100% sure what you'll see in the future. We've kind of stuck with X, so we'll stay with that. For angular displacement, we're talking about the change in the angle. And of course, we always use theta as a base angle thing. So if I have a circle, something like this, this is my angle theta. It's going from there to there. So when I want to talk about how much theta has changed, I need to know the radius. So therefore delta x is equal to r times delta theta. That's the way to convert back and forth between linear and regular. Okay, now, where we had linear displacement, we also had linear velocity and angular velocity. So the same way there was a corresponding thing before, well, we know that v is equal to delta x over t, and we used v to represent linear velocity. For angular velocity, we're going to use the Greek letter omega. It looks like kind of a script w. Omega is going to equal delta theta divided by t. Now, there's a couple common units that we'll see with that. Probably the most common one we'll see is radians per second. Which radians would represent how much of the angle changed, and t would represent the time for that angle to change. But we can also see revolutions per minute. So it's important to understand, because that's a fairly easy thing to calculate. So let's actually go ahead through and work our way through. Let's do a simple calculation with that. Let's say something is spinning at 10 revolutions per minute. Now, when you see RPMs, I think the best way to write it is this way, because it makes it easiest to solve. I'm going to multiply by 1 to get rid of minutes. I need minutes on the top. I want seconds on the bottom. 1 minute is 60 seconds. If I quit right there, I'd have revolutions per second. The last thing I got to do is get rid of the revolutions. Revolutions go on the bottom to cancel it out, and I want rads on the top. And I know that 1 revolution is 2 pi. So what I end up with is 20 pi radians divided by 60 seconds. And of course you can simplify that. Excuse me. So you could actually figure that out very carefully, and you'd get pi over 3 radians per second if I did my math right. This is the thing where you could leave it in pi, but you also know pi is 3.14, so you can also make that change. Now, the same way, now to convert, well, it's going to be the same thing. Linear v is going to equal r times omega. This would be the speed tangent to the circle if I know how fast it's rotating. So that's important, and we'll use it. Angular velocity, of course, omega is going to be in rads per second most of the time. Doesn't have to be, it can also be in RPMs. So be prepared for that. Okay, the last thing, obviously there was a third thing we talked about with motion a lot, and that's acceleration. So we have linear acceleration and angular acceleration. Now we know that linear acceleration, a is equal to delta v over t. Well, this angular acceleration, we use alpha, and alpha is equal to delta omega divided by t. So it's actually still the same thing. Now, to figure out the direction of the angular acceleration, we're going to use a right-hand rule. It's not the only right-hand rule you'll see in physics, but it's the one right here. So if I have something, and again, this is three-dimensional, so it's a little hard to see. So I have something like that, and objects are rotating around it that way. Then the fingers represent linear v, which is, of course, tangent to the circle, and then thumb represents alpha, angular. So what happens is if I go like this, my fingers are wrapping up out of the page, my thumb is pointing to the right. So I figure out which way it's curving. So if it curves into the page, my thumb would go the other way. So that's one right-hand rule. It's not the only right-hand rule you'll see. There are other ones you will see. Okay, let's compare the two, and then we'll do an example problem. The variables. Well, for displacement, our variable is x. And x is equal to r times theta. Now, watch here, it's kind of a neat thing. So over here, our displacement in the angular world is theta, and theta is equal to x over r. Now, we know velocity in this world, in the linear world, is v, and v is equal to r times omega, which is angular velocity. So angular velocity is equal to v divided by r. Now acceleration, linear acceleration is a. A is equal to r times alpha. I may not have said that a second ago. The linear acceleration is r times the angular acceleration. So if I need to find the linear acceleration of a point on a wheel, I simply take the radius times the angular acceleration. And alpha is equal to a divided by r. And of course t is just t. That doesn't change in any world. Now here's a shortcut to help you with this. These three have been ingrained into your head, x, v, and a. Take a look at their angular components, their angular corresponding parts. Theta is equal to x over r. Velocity, angular velocity is v over r. Angular acceleration is a over r. So all I'm doing is taking the linear component and dividing by the radius of the circle. So therefore, that's kind of an easy way to remember it, since r is on the bottom of each one of those. All you're doing is taking your things you already had and dividing them by r to get their angular corresponding counterpart. Now let's take a look at the linear equations we had before. We had VF is equal to VI plus AT. Well, the angular corresponding with that, well, the angular correspondent to V is omega, so omega final is equal to omega initial plus angular acceleration times time. So it's the same equation, it's just got omegas and alphas in place of it. We have x is equal to VIT plus 1/2 AT squared. Powerful equation that we use a lot. Well, the angular component of this, well, this x is theta, remember, that's how much the angle has changed, is equal to omega I times t plus 1/2 angular acceleration times t squared. So again, it's the same exact equation, except I'm putting in angular variables instead. The last one, again, which we use a lot, Vf squared is equal to Vi squared plus 2a delta x. Well, over here, x is omega. Omega final squared is equal to omega initial squared plus 2 times alpha times delta theta. So all I'm doing, same exact equation, except I'm putting in the linear components of it. Now let's do a simple sample problem. We'll do more in class, but let's do at least one so you have it. Let me see if I can find one. So a bike wheel of radius 20 centimeters, 0.20 meters, accelerates uniformly from rest to 10 RPMs in 5 seconds. What is the final omega? Well, for part A, what I need to do, you might want to stop it right there and copy down the question, leave yourself to answer it. Or you can listen to me and try and keep up. So we go 10 revolutions per minute. Now again, to solve it, you want to write revolutions per that. That's equal to omega final. But I want to get it in radians per second. So what I'm going to need to do is convert that. I'm going to have to go, let's multiply. Well, I want to get rid of minutes. I want seconds, and I know 1 minute is 60 seconds. Then I'm also going to multiply that again. I want revolutions gone now, and I want rads on the top. And I know that 2 pi is equal to 1. So what I'm going to take is 10 times 2, which is 20 pi. So I get 20 pi radians divided by 60 seconds. Everything else cancels out. The revs cancel out. The minutes cancel out. And of course, that's pi divided by 3 rads per second. Now, you can easily convert that. You're going to get a little over like 1.05 rads per second. So you don't have to leave the pi in there if you don't want. For part B, what is the linear velocity of a pebble stuck in the tread of the tire? So in other words, oh, sorry, that may have been out of the screen. I'll pull it up there so you can catch up with it. Apologize for that. If I have this as the center of my wheel and the wheel's rotating, I want to know the linear speed of this pebble. Of course, we know that's going to be tangent to it. V is equal to R times omega. I know that this is 0.20 meters. That's my R. So V is equal to 0.20 meters times 1.05 rads per second. And I can just multiply that out. 0.2 times 1.05 is going to be approximately 0.2. Since I'm multiplying by 1, it's not going to change a whole bunch, a little bit. 0.21 meters per second. So kind of nice to do that. So finally, the last thing I want to get is the angular acceleration. I want to get alpha. Excuse me. Alpha is equal to delta omega divided by time, which is omega final minus omega initial divided by time. Omega final we know is 1.05 rads per second minus 0 because it started at rest divided by 5 seconds. 1 divided by 5 is approximately, I'm not going to do it with the calculator, 0.2 radians per second squared. Cool. So every linear thing we did has a corresponding rotational thing that goes with it. And rotation is big. It's important in your everyday life. The wheels on the bus go round and round.